Alright, hello. Doesn't look like anyone's here yet. So maybe I'll give it a minute. See if anyone pops in the next minute or two. Otherwise, we'll start then. So actually I'll restart this timer here. For another couple minutes. And if no one shows up by the time it's done, we'll just get started. Alright. Good afternoon. Hopefully you're had a good weekend there. Alright. Let's see here. Let me unmute that. Is there a destruction zone behind me? I think so, but I cover it up, so it's all good. Alright. So we're now into sort of one of my favorite things about calculus here, which is this Maclaurin series, Taylor series, power series stuff. Yeah, it's traditionally, single variable calculus is actually a 2-semester class traditionally. Denison does it a little bit different. So it's kind of at the end here. But this is just definitely one of my favorite, and actually one of the most important parts of calculus. Because this is really how you do a lot of computations. Because you usually can't do an integral of some function that you just come up with. So this is how we do it. Right, so we'll touch a little bit on that in problem 4. But for now, let's just do some basic finding power series representations. Right? So problem 1 is we want to find a power series representation for the function 1 over x plus 2. Right? So to do this, well, for this first one, we could of course go through the Maclaurin series process on this one, but that's not going to be the quickest way about it. The easiest thing to do here is to try the geometric series trick that we had. Right, so take a second and see if you can get this to look like the sum of a geometric series. Is there some way you can manipulate this function here into the form a over 1 minus r? Right? Try that out for a second and see if there's a way you can do that. So ultimately, you can work it into a form like this. So if you just try sort of piece by piece to get this to what you need, so a over 1 minus r, the first thing you want to do is try and get this 1 right here. Right? That's the most important piece, because that's the tricky one to get. Right? But once you have that, it actually becomes a bit simpler. Now you're just sort of putting everything in the right place. So once we get this 1 right here, right, this 2 on the bottom, I'm essentially just shoving it into the numerator instead. Right? So the 1 turns into a 1/2 up here. And then I need it to be 1 minus something. So here I just put a double negative. Right? And that turns the plus into a negative. Right? Does that seem about right for what you have? Hopefully. And then once we're here, we can now just apply, sort of undo the sum of the geometric series. Right? Oops. So remember, this is the sum from 0 to infinity of a r to the k. Doesn't look like a good infinity. Right? So we just undo this into this form. Right? And that's all there is to it. So here we get the sum, k equals 0 to infinity. This is a, so we'll put our 1/2 here. And then r to the k is this stuff in the parentheses right here. Minus x over 2 to the k. All right. Usually, we like to sort of unpack this a little bit and get the x to the k part by itself, so that we sort of have like the coefficient piece and then the variable piece. So if we unpack it a little bit, right, the top here becomes minus 1 to the k, x to the k. The bottom, this is 2 times 2 to the k, right? So we could just skip right to this being 2 to the k plus 1, but I figured it'd be a good idea to write it separately. Right, so we have negative 1 to the k over 2 to the k plus 1, x to the k. Right, so this stuff right here, this is your coefficient of the power series. Right? So the way we've set this up, the center of this series equals the center, which normally we call a, is 0 here, right? Because it's just x to the k. Now it's possible to do some other sort of rearrangements of this series as well. So this is why the question sort of phrased as find a power series representation for this. Because, another thing you could do if you were so inclined and wanting to be clever with this, right? Something you could do here is split off one of these. So write this as 1 plus, x plus 1 here, right? And then you could say, all right, well, that's 1 minus negative x plus 1. And now, more simply, this is, let's see, from k equals 0 to infinity. A here is just 1, so this would be negative x plus 1 to k. Or if we split it off, this is sum from 0 to infinity of negative 1 to the k, x plus 1 to the k. Right? So now this one here, this one's center is, remember the center is x minus a, so this center is negative 1. Right? So there's a few ways to go about this. Okay? Hopefully that makes some kind of sense. Here, we know that this is going to converge for absolute value of x less than 1. Right? That's sort of what the geometric series tells us. Oh, sorry, not x. I said that wrong. R here was negative x over 2. So it's actually going to be absolute value of x over 2. Right? As long as that is less than 1. Right? We can ignore the negative because the absolute value will get rid of it. Here, this converges when absolute value of x plus 1 is less than 1. Right? So there's an interesting difference between where these two series are valid. Right? This one here is going to be valid from negative 2 to 2. That's what this inequality translates into. This one here is valid from minus 2 to 0. Right? Did I get that right? Yeah. Right? So, you get a bit of a simpler series, but it's valid sort of for less, it's valid at less places. Right? So, any questions at all about this one here? For what it's worth, I think the first one is a better choice, but they're both, I just wanted to show a couple interesting ways to go about this. Any questions? Right. Again, let me just emphasize that the second one here, this is just an alternate solution. All right, let's look at problem 2. All right, problem 2 is asking to find a power series representation for this function. All right. So think about that for a second. Try and think if there's any quick way you might be able to go about that. So, any thoughts on what we could do about something like this? There's a few ways you can interpret how to solve this. So one way we could do this is similar to what we did in the first problem. We do some manipulations to this and turn it into 1 minus negative x over 2. And on top, instead of just being 1/2, it will be x cubed over 2, right? And so this is your a, this is your r value, right? This is certainly one way to do it. Another way to do it is to recognize that this is just x cubed times this function. Right? So it's x cubed times this thing that we already have a power series for. So we'll say, all right, well, that's x cubed times, let's see, what is this series? Let's steal this here. Duplicate it, thank you. Okay. So it's this, which we can take this x cubed and multiply it to the inside here because it doesn't have a k in it. Well, it can't have a k in it, right? Because it's outside the series. And we'd end up with this. And there you go. Now, it's pretty common to want just a x to the k here instead of k plus 3. Of course, there's nothing specifically wrong with this as it's written, but typically we like to keep this as like just a, as simple of a thing as we can. Again, let me emphasize that there's nothing actually wrong with this expression. But should you want this to be just x to the k, we can re-index this. And here, this means I want this number to go down by 3. And if I want this number to go down by 3, then I have to raise this number by 3. Right? So let me box this because this is perfectly fine. But here, right? So again, I want this to go down by 3, so I push this up by 3. Right? So again, pushing this up by 3 is going to cause every single one of these to go down by 3. So this will be k negative 1 to the k minus 3. 2, this is going to be k minus 2 down here. And then this will just be x to the k. Right? So, you have a lot of options here of how to sort of write this out. And even this, there's all sorts of manipulations you can get into with these. But, I just wanted to sort of, again, show a couple different options we have here. Right? But as far as this goes, any questions about sort of getting from here to here at all? All right, awesome. So let's look at problem 3 here. Right, so problem 3 is I want a Taylor series, a power series for this function right here. Oops, well, it doesn't really matter if I write 1 plus x or x plus 1. I'll write it this way though. Right, so how do I get this? Well, if this is f of x, okay, then f prime of x is going to be 1 over 1 plus x. Okay? So I can start by finding a power series for this thing and then try to integrate it. So 1 over 1 plus x, right? We're going to use our geometric series trick here again. Right, so this is just negative x to the k, which is simply, again, it's a good idea to separate out your coefficients from your powers of x. Right, so there's a nice simple power series here. And now we're going to integrate this. Right? So if we take the antiderivative here, we'll get to this plus some arbitrary constant, right? So let's see, let's integrate this 1 over 1 plus x dx. Right? Let's see here. So this will be the sum from k equals 0 to infinity, minus 1 to the k, x to the k plus 1 over k plus 1, plus c. Right? Let's call this capital F of x. Right? Just to maybe, well, let's call it g of x. Probably a better idea. Right? So g of x, this is equal to ln of 1 plus x plus some constant. So what we're going to do is we're going to say, all right, well, f of 0, okay, this is ln of 1 plus 0, which is ln of 1, which is 0. So in order for, right, so we want to choose c so that f of x equals g of x. Right? That's our goal. So in order to do that, we plug in 0 to g and try to get the same answer. Right? So plug that in. This is 0 to the k plus 1 over k plus 1 plus c. Right, now the important thing here is that this is 0 to the k plus 1 power. So we never wind up with 0 to the 0 here. So this whole series is just 0. Each term is 0, so it all goes away. So this is 0 plus c, and we need to set that equal to 0. So this implies that c has to be 0, and therefore ln of 1 plus x, well, we can just take this series right here and replace c with 0. So basically get rid of c here. So it's the sum from k equals 0 to infinity of negative 1 to the k, x to the k plus 1 over k plus 1. Okay, and there we go. There is a power series for ln of 1 plus x. Right. Any question at all about this one? Maybe zoom into the whole problem here. How does that look? Questions about this? Awesome. This isn't too bad. Let's go ahead here and look at problem 4. Right. Problem 4 has some interesting stuff going on. Come on. Right. So in problem 4, we want to find a power series for sine of x squared. Right. So think about how you could do that. How can we find a power series for sine of x squared? I'll let you think about that for a second. I'll actually be right back while you think about this. All right. So, any ideas on how we could go about this one? Well, if you're a bit unsure, let me remind you that sine of x, right? We computed the Maclaurin series for this in the lecture videos. The powers are well, it's still a power series. Right? So representation of this is -1 to the k, x to the 2k plus 1 over 2k plus 1 factorial. So if that's sine of x, can you think of any way we could get sine of x squared from that? Well, to get sine of x squared from sine of x, you just plug in x squared here, right? So we can do the same thing. Just plug in x squared for x. We have -1 to the k, x squared to the 2k plus 2, or 2k plus 1, sorry, over 2k plus 1 factorial. And then all we have to do is just pull the square out of the parentheses. This is k equals 0 to infinity, -1 to the k, x, this is going to be to the 4k plus 2 over 2k plus 1 factorial. And that's that. That's a power series for sine of x squared. So, one reason we might want to do something like that is something we learn in Calc 1 is that this integral here, integral of sine of x squared, is something we can't do. right? There's no elementary function way to write this down, right? To write down the integral of this. This is what we call an integrable function, right? So that's not to say that, you know, if we tried to find the area under this function or something like that, it wouldn't exist, right? This function does have an antiderivative. The problem is it's not what we call an elementary function, right? Now, what do we mean by that? Well, things we can build out of functions like this, right? Sine, like trig functions, logarithms, exponential functions, polynomials, algebraic functions, all of that kind of stuff, those are considered elementary functions, right? So you have, you know, transcendental and non-transcendental versions of it, but they're all elementary functions. They're things we can write down simply. This is not an elementary function. There's no nice closed form way to write it down. However, we can express it as a power series. And that's the nice thing here. Sorry, I meant to write integral of this. So if we just integrate this series here, not x, k plus 2. There's a k there. 2k plus 1 factorial dx. Right, so remember, to do the integral, we just integrate this term by term. So we're going to get sum from k equals 0 to infinity, minus 1 to the k, x to the 4k, this is now going to be plus 3, over 4k plus 3, times 2k plus 1 factorial plus c. Right? So whatever this thing is, right? So there's no nice way to write this series down. It's just, hey, here's some series, right? Whatever this is the integral of sine of x squared. This right here is an antiderivative of it, right? Again, there's no way to rewrite this series and say, here's some nice function that this is equal to. And that's because this is not an elementary function, right? But it's a function that still has an expression, namely this right here, right? Any questions on this one? I think this is a really important concept here, that, you know, we can still work with this function. We can still integrate this function, right? In fact, you can even put bounds on this integral, plug them in here, and try and, you know, see what this series converges to. More than likely, you're just going to take some approximate values of what this series is. In other words, like cut it off at some high value of k. Use Mathematica to compute the sum from k equals 0 to 1,000 maybe. There's all sorts of things you could decide to do to get an approximation. Any questions? Awesome. All right, if there are no questions, let's go on to the next problem. Problem 5. Right. So problem 5 here says, let's find a Maclaurin series for cosine of x. F of x is cosine of x. So we're going to do the same thing I was recommending we do in the lecture videos, which is where we make this table and try and find a pattern here. Right? So here I'm going to say k. Right? The kth derivative at x. And then the kth derivative. Here we're finding a Maclaurin series, so we're finding it at 0. Right? And we want to do this for enough k values to sort of understand what's going on. So as many as you need. Right, so if we start with cosine of x, the first derivative is negative sine x. Then we go to negative cosine x, and then we go to sine x, and then we're back at cosine. Right? And you can see, this pattern is just going to repeat. Right? The seventh one is going to be sine x. Right? So it has this sort of period of 4. Every 4 derivatives, we're back to where we started. Right? So if we plug in 0, here we're going to get 1, and then 0, and then negative 1, 0, 1, 0, negative 1, 0. Right? So much like sine, we get this thing where it's every other term is 0, and then we have kind of an alternating pattern here. So, again, what I highly recommend here is just writing out the Maclaurin series and, just write it out first and then get rid of anything that's 0. So in this case, what you're going to have is that f of x equals, so here we're going to have 1 plus 0, right? And then minus 1 over 2 factorial x squared plus 0, right? Because we're going to have a 0 here. And then plus 1 over 3 factorial x cubed plus 0 minus 1 over, oh, sorry, not 3. This is 4. Minus 1 over 6 factorial x to the 6, and so on, right? So if you follow this pattern, what we're really going to have is 1 minus 1 over 2 factorial x squared. Remember here, these numbers that I'm writing, we're always dividing these by the factorial, because remember, ck is the kth derivative at 0 over k factorial. That's how these go in a Maclaurin series. So that's why I'm writing these factorials here. So 1 over 4 factorial x to the 4th minus 1 over 6 factorial x to the 6th. And you can check, and you probably won't be surprised, the next term is 1 over 8 factorial x to the 8th. Right? So, how do we write this down as a series? Well, this is going to start at 0. Right? The top is it's an alternating series that starts on a positive note. So it's minus 1 to the k. Right? The powers of x are all even. Right? This one's 2 times 0, 2 times 1, 2 times 2, 2 times 3, 2 times 4. So this is x to the 2k on top. And the factorial always matches the power. So it's over 2k factorial. And again, it's essential that you put parentheses around the 2k here. Because again, 2 times k factorial is not the same thing as the factorial of 2k. Right? Just keep that in mind. So this here, this is the Maclaurin series for cosine of x. Right? It's a great idea to, if you're going to memorize any Maclaurin series, you want to remember the ones for e to the x, sine of x, and cosine of x. Those are the 3 most important ones by far. Right? So any questions here about this first part of the problem, which is finding the Maclaurin series for cosine? Any questions here? Awesome. All right, so let's check this next part, which is let's verify that this is the derivative of the Maclaurin series for sine of x. Right? Because we know cosine is the derivative of sine. Does this still work if we look at it as a Maclaurin series? Right? Well, oops. So we're asking here, we're trying to take the derivative of sine of x. And we're saying, all right, well, let's look at this as a Maclaurin series. So d dx of the sum from k equals 0 to infinity of the, let's see, sine of x, remember, is negative 1 to the k, x to the 2k plus 1 over 2k plus 1 factorial. Right? So with that in mind, we want to differentiate this. So let's do it. Differentiate this. Remember, we can differentiate term by term. So k equals 0 to infinity. This x to the 2k plus 1 is the only part that's actually has variables in it. It's a function to differentiate. The rest of it's just a coefficient. So we're going to let all this stuff sort of just be as it was. To differentiate this part, right, that 2k plus 1 comes down, x, and then we subtract 1 from the exponent. That's just 2k now. But let's simplify this, right? This part's going to cancel this and cut it down to just 2k factorial, right? It's cutting off that last term of the factorial there. And so this is just k equals 0 to infinity, negative 1 to the k, x to the 2k over 2k factorial. Ta-da! Right? So any questions about that part? All right, so my challenge to you here is show that the derivative of the Maclaurin series for cosine of x is still sine of x. It is true. Verify it. Right? And while you're at it, you can also look at the Maclaurin series for e to the x. Show that's still e to the x. All right. So I want to talk about this last problem here because this is really, I love this problem. This is one of my favorite things to do with power series. Right? There's a very important formula in math. This is called Euler's identity. And so many things are named after Euler, but Euler's identity, which says e to the I theta is cosine of theta plus I sine of theta. Right? And you can use x instead of theta here if you want. It's not a big deal. Right, let's prove that this is a true statement. Right, so again, remember that I is the square root of negative 1. This is the imaginary number I. Right, so how do we do this? Okay, so we need to know all three of those Maclaurin series to do it. Right, so first things first, let's write e to the I theta. Okay. Using the Maclaurin series for e to the I theta, I can tell that this is going to be the sum from 0 to infinity of I theta to the k over k factorial. Okay? Now what I want to do is I want to just write this series out. Right? So what I'm going to do here is just write out, let's write out, I don't know, 8 terms of this. That should be pretty good. So plug in 0, and we're just going to get 1. Right? Plug in k equals 1, and we get I theta. Right? So I'll write I times theta. Right? Plug in k equals 2, and we get I squared theta squared over 2 factorial. Right? And then I cubed theta cubed over 3 factorial. Right, this won't be super interesting yet. I to the 6 theta to the 6 factorial. Maybe that's enough. All right. So now let's start getting rid of all these duplicate i's. Right. So I to the first is just I. I squared is going to be -1. Right? Because that's square root of -1 times square root of -1. I cubed will be negative square root of 1, so -I. And then I to the fourth is just 1 again. Right? And then it repeats. I to the fifth goes back here. I to the 6, 7, 8, 9, 10, 11, 12, so on. Right? So we can simplify this a bit. This will be 1 plus I theta minus theta squared over 2 factorial minus I theta cubed over 3 factorial plus theta to the fourth over 4 factorial minus, let's see, we're here, minus I, plus I theta to the fifth over 5 factorial minus theta to the 6 over 6 factorial. And if we follow the pattern more, we're going to get minus I theta to the 7th over 7 factorial plus theta to the 8th over 8 factorial. I wanted to get 8 terms, but I ran out of room up there. Right? Okay, so now that we have this, there's 2 types of terms here, right? There's terms that are purely real, and there's terms that are purely imaginary. Let's group those. So all the blue terms here, these are all purely real terms. There's no imaginary number at all. All the ones that I'm putting red brackets over, these are all purely imaginary, right? They all have an I in it. All right, so let's group these. We're going to have 1 minus theta squared over 2 factorial plus theta to the fourth over 4 factorial minus theta to the 6 over 6 factorial plus theta to the 8th over 8 factorial. Right? And then there will be more real terms like this. So I'm going to write plus ... And then we're going to switch over to the ones with red. This is plus I theta. In fact, let's factor out the I from all of these. Right, so all of those terms have an I in it. I'm going to factor it out. Right, so we'll have theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial minus theta to the 7th over 7 factorial, and then that pattern continues. But look at what happens here. Look at what this is and what this is. Hopefully you recognize these infinite series that we've come up with here. This one in blue is exactly cosine of theta. Right? This one inside the parentheses here in red, that's exactly sine of theta. So this is plus I sine of theta. So we verified that e to the I theta is just cosine theta plus I sine theta. Right? It's really quite remarkable. Right? And this is where you get this famous formula, which is, let's see, what do I want to plug in here? E to the I pi equals -1. Or e to the I pi plus 1 equals 0. Right? It's been called the most beautiful formula in mathematics because it uses e, I, pi, 1, and 0. Right? It gives a relationship between them all. And it's really surprising that something like this should be true. And it's all because of this identity right here. All right. So are there any questions at all? Well, I hope you're having a good week, had a good weekend, and your week's been all right so far. I hope you're doing well, and yeah, I'll see you tomorrow. A good one. We'll start the next stream or the next session in about 7 minutes. Take care. Let me know if you have any questions. All right. Let's get started. All right. Let's get started. All right. Let's get All right. Nothing. Let's see. Cool. We'll right here. All right. So let's just jump right into this. Yeah. So this power series stuff is fantastic. It's really sort of one of, I think, the most interesting topics in calculus here, because it allows us to sort of deal with functions that don't sort of represent themselves nicely, and it's how we can do calculus with them. It's also how we can sort of, it's realistically speaking, this is how we can approximate values of functions and try and fit sort of, real world data to a function that we can perform calculus on. Right? So let's start here with problem 1, which is saying let's find a power series representation of this function right here, 1 over x plus 2. Right? So there's a couple different ways to do this. Let me let you guys try and see if you can come up with a way to represent this as a power series. Okay? So give you a second, think about that, and see what you can do. So there's a few approaches to this. Of course, you could always go down the road of trying to write out a Maclaurin series for this, or Taylor series if you already know what that is. But I think the simplest answer here is to do none of those things and try to represent this as a geometric series. So to do that, we have to get, an a over 1 minus r type deal going on. So how can we do that? Well, when we're trying to turn this into this form, the most important thing to get is this 1 right here. Because once you have that 1, the rest of this is just going to fall into place. Right? So here's what I'm going to do. Right, so I'm going to change the order of these first off, just so it kind of looks like this. But I'm going to factor a 2 out of the bottom. So this is 1 plus x over 2 now. Right? Great, I have a 1 there. Now I'm going to take this 2 and I'm going to push it into the numerator. Right? So that's going to cause me to have a 1/2 on top and 1 plus x over 2 on the bottom. All right. Now, the other part is I need it to be 1 minus something. This is 1 plus something. What can I do, or any suggestions on what I could do to change this plus into a minus? Or in order to get 1 minus something? See what we can do there? we really want a minus there, then, oh, switch to highlighter on me. If I really want this minus, then I just put a double minus. Right? If I just use a double negative like this, if I multiply this back out, right, it's going to be 1 plus x over 2 again. But if I split it out like this, then I have my 1 minus that I want. So look, here's A. Here's R. Whoa, what just happened there? And so we can make a power series, right? We can turn this back into a geometric series. This is the sum from k equals 0 to infinity. Remember, a geometric series is a times r to the k. So it's a, which is 1/2, times r to the k. And there you go. Right, you can split this up a little bit. It's usually a good idea to try and get like the coefficient part separate from the, x minus a to the k part if you can. So if we split this up entirely, you're going to wind up with -1 to the k, x to the k on top, times, down here you're going to have 2 times 2 to the k. Right, because you're going to have this 2 right here times this 2 to this k power right here. And so if we combine those together, we'll get -1 to the k over 2 to the k plus 2 to the k plus 1 times x to the k. Right? So let's point out a few things about this function here, or this series here. What is the center of this power series? Normally write this as A. For what the center of this thing would be?
Is it x?
It's not x itself. So remember, a power series comes in the form c to the k x minus a to the k. So it's this number that's inside the kth power with x. In this case, the center should be 0. Right? Because this is like x minus 0 to the kth power. So basically, if you only ever have like x to the k or x to whatever power you're dealing with, the center is going to be 0. If you have like x minus 4, then the center would be 4. That's what the center of this is 0. Now, if we use the rules of geometric series, we can see sort of what interval this converges on. Right? So here, remember, for a geometric series, it converges when absolute value of r is less than 1. So here, we're then saying absolute value of -x over 2 is less than 1, which tells us absolute value of x less than 2. And so the interval on which this converges would be from -2 to 2. Okay. I want to show you another way that we could actually have solved this problem. I think this is the better way to do it because this power series is going to be valid on, as it'll turn out, a bigger range than the other one. But another way you could have solved this problem that's perfectly reasonable is, here we have x plus 2, right? Another way you could approach this is to just split this 2 into 1 plus 1. So I'm going to write this as 1 plus x plus 1. Right? And then that's 1 over 1 minus negative x plus 1. And now we can apply the geometric series rules to this, where a is 1 and r is all of this. So it's the sum from 0 to infinity of a, which is 1, times negative x plus 1 to the kth power. Right. And again, splitting this off, or splitting the coefficient part here, which basically just means factor out that negative, you're going to get negative 1 to the k, x plus 1 to the k. All right. So what's the center of this thing? What's the center of this power series?
Negative 1? No,
Yep.
1.
Yeah, this would be negative 1. Because this would be x minus negative 1 in here. Right? And if we tried to find the interval on which this converges, again, we look at absolute value of r less than 1, which says, all right, absolute value of x plus 1, or negative x plus 1. That negative doesn't really matter here. The absolute value will kill it. Less than 1. Right? So, sure, let's get rid of it. So absolute value of x plus 1 is less than 1. That turns into, right, we can go 1 below negative 1, and we can go 1 above negative 1. So this series, the interval on which this series is valid, is from 2 to 0. Or sorry, negative 2 to 0. Right? And that's all because the center is different. And in the videos that I finished recording right before the problem session here, so I'll put those up right afterward, we talk about radius of convergence, and you'll kind of see why this expression here, this power series, has a much bigger interval than this one down here does. Right? You'll notice they both end on the left side at negative 2, and that's conveniently where this function's not defined anymore. Right? So see if you maybe can think about what's going on there. And then you'll get the answer to that in the video. Okay. So any questions at all about problem 1 here? Okay. So now we kind of did the problem 2 separate times, and they're both, each one of these is an answer to the problem. I just want to say, you have a few choices in how you want to do it. Any questions at all? Awesome. Okay, so let's look at problem 2. Right? In problem 2, we're asking for a power series representation of this function, x cubed over x plus 2. See if you can come up with any ideas on how to do that one. So just like the last problem, there's a couple ways we could approach this. One way is to do the exact same thing we did, in the first case, or, the same way we did the second one as well, the second version of it. Say we do the first one, oops, not x squared, x cubed, over 2, 1 minus negative x over 2. Right, this will work out just fine. Right? And then, the top here, this would be your A, this would be your R. This is a perfectly acceptable way to do it. An even better way, I think, is to say, well, this is x cubed times something I know the power series, or know a power series for. Right? So just x cubed times this thing. And then, well, we know the power series for that thing, so let's write it down. Right? That's k equals 0 to infinity, negative 1 to the k, 2 to the k plus 1, x to the k. Right? And, once we have that, we can just take this x cubed right here and multiply it into the series. That's it. Sum from k equals 0 to infinity, negative 1 to the k, over 2 to the k plus 1, x to the k, it'll be k plus 3, right? K cubed times x to the k, wow, I can't speak. X to the third times x to the k, we just add the exponents. If you say something enough times, eventually the right iteration of words comes out. Right. And there you go. So we can sort of use previously known series to create new series, right? By multiplying or dividing or stuff like that. Right? Any questions about this one at all? This coffee's getting cold, and cold coffees. At least coffee that's like hot that cooled down. All right. So, there's no questions about this one. Let's look at problem 3. All right. In problem 3, we want to find, I'm going to call this one f of x. We want to find a power series for ln of 1 plus x. Okay. How do we find a power series for this? Any thoughts on how we can go about that? Again, there's a couple options. One of which is considerably better than some of the others. So one option here is to go through the Maclaurin series process. right? Take multiple derivatives of this, and go from there. But ln, in particular, there's a better way to do their power series. So if we take this, and we are going to take a derivative here, but just one. And the reason we want to do that is we end up with something like this. Well, this is exactly the derivative, right? But the point of it is, the derivative of ln here, it's going to turn into something that we can get a power series for using the geometric series trick. That's the really nice thing about ln and finding power series. Right? The derivatives turn into something that we can use the power series trick on. So if we find a power series for the derivative of ln, and then we integrate it, we can get back to a power series for this. Now there'll be a little bit of work involved, but it'll probably be less work than trying to do the Maclaurin series approach. Right? So let's go ahead and do that. So 1 over 1 plus x, right? We just need to rewrite this a little bit. So we're going to use that exact same trick from earlier. Get 1 over 1 minus negative x. And so we can turn that into a geometric series, which looks like this. Right? And let's split this up into a coefficient part and power of x part. And there we go. So this is a power series for the derivative of ln of 1 plus x. So now, if we just integrate this, then we can start getting toward a power series for ln of 1 plus x itself. Right? So let's integrate this. So integral of 1 plus x dx. This is the integral of k equals 0 to infinity of negative 1 to the k, x to the k, dx. Right. So one thing to keep in mind is this expression here, remember, is really only valid for absolute value of x less than 1. Or in other words, on the interval minus 1 to 1. Right, so it's not valid on the whole domain of this function. Anyway, so let's integrate this. Remember, to integrate a power series, we can just integrate term by term. Right? So this is the sum from 0 to infinity, and we'll get negative 1 to the k, x to the k plus 1 over k plus 1. Right? Because that negative 1 to the k is a bit irrelevant for this part, or for the integral, because it's just a constant. So we get this, and then of course, plus c. Right? Let me call this function here, this antiderivative, let's call it g of x. Right? Because what we want to do is we want to choose c so that g of x equals f of x. Right? Right? Because right now, this right here, if we ignore the plus c here, this is an antiderivative of 1 over 1 plus x. But ln of 1 plus x is another antiderivative of 1 over 1 plus x. So if you remember back to single variable calculus, or Calc 1, or 135, or whatever your form of it was called, two different antiderivatives of a function differ by a constant. So if we can find the appropriate constant here, we can make this series, in fact, equal to this. So what we start by doing is plugging in 0 to this function here to see what we need it to be. Right, so f of 0, that's ln of 1 plus 0, which is ln of 1. which is 0. Okay? So that means when I take this expression and I plug in x equals 0, I need to choose the constant so that the output is 0. Right? Does that make sense? Right? So g of 0, this is going to be the sum from 0 to infinity, minus 1 to the k, 0 to the k plus 1 over k plus 1 plus c. If you look at this term right here, every single one of these are going to be 0. These are all zeros. Right? So this is just c. And we need this to equal 0, so we get our c value. C is 0. Therefore, ln of 1 plus x is just equal to this, equal to this right here with c equals 0. So this is exactly given by the sum from 0 to infinity, minus 1 to the k, x to the k plus 1 over k plus 1. Right. Bit of a fun process, I think, here. Right. Any questions at all about this? Hopefully this makes sense here. All right. So let's go on then to problem 4. Why am I so zoomed out? So problem 4, we want to find a power series for sine of x squared. Any thoughts on how we could approach this? You can think up something here. So if you haven't come up with any ideas yet, let me give you a hint. Remember that the Maclaurin series for sine of x is given by the sum from 0 to infinity, minus 1 to the k, x to the 2k plus 1 over 2k plus 1 factorial. So we covered that one in the lecture video. See if you can use that as a way to get a power series for sine of x squared. Do you have any ideas about that? Any thoughts on what we could do?
We can plug x squared for x.
Yeah, exactly. Right, this is just a function of x here. So if I swap x, this right here is basically we're just plugging x squared into the sine function. So let's do exactly that with the Maclaurin series. Right, so sine of x squared, we're just going to replace all the x's here with x squareds. So it's the sum from 0 to infinity, minus 1 to the k, x squared to the 2k plus 1 over 2k plus 1 factorial. Yeah, that's exactly it. It'll be a good idea here to multiply this out here, because we still want to write this as x to some power. But yeah, that's exactly it. So this will be 4k plus 2 here, divided by 2k plus 1 factorial. And there we go. That's a power series for sine of x squared. So once we have that, now we can perform this integral here. Right? So you might have learned, in the last calculus class you took, that we can't integrate this. Well, the correct statement is there's no sort of elementary function we can write down which is the antiderivative of this, right? There's no way that can be done. But this is a perfectly integrable function. It meets all the requirements to be integrable. In fact, it's continuous, right? We can integrate a continuous function. The problem comes in with, well, what is the antiderivative? And that's something we couldn't do before, but using this Maclaurin, does this still count as a Maclaurin series? I'm not so sure about that. Maybe. But using this power series here, we can, for sure, compute the antiderivative. It's just going to be it's going to give us a power series as the output, right? We can't get a nice, elementary function, elementary being, some algebraic function, trig, exponential, logarithmic, right? The usual kind of functions we have. It's not going to be one of those. It has to be expressed as a power series, but it's still a function, right? So to integrate this, we swap over to the integral of the series. Oops. X to the 4k plus 2 over 2k plus 1 factorial. And this is why I really, really like power series, because it allows us to work with anything, right? Now, they might only be valid on certain regions. This one here is valid everywhere, from minus infinity to infinity, so that's kind of nice. So this is 100%, unambiguously going to be the antiderivative. But yeah, there's just so many interesting things that happen here. Right, so let's integrate this. Remember, when we're doing an integral, we can just integrate term by term. So 0 to infinity. Integrate this, we get -1 to the k. X to the 4k is going to be plus 3 here. Now we need to divide by 4k plus 3. And that's going to be times this factorial. And then plus c. And there you go. That's that. Right? So whatever this is, it's the antiderivative of sine of x squared. Again, it's not particularly pretty, right? It's not going to be something we can write down as a nice function. It is this thing here. But the point is we can do it, right? And, if you want to put some bounds on this, well, we just evaluate the series at those different x values. Now, of course, chances are we're not going to be able to explicitly get those numbers, right, for the full power series here, when we plug in, say, like -1 to 1 or something like that. But what you can do is do an approximation, right? So take like the sum from k equals 0 to 1,000, say, right, and get like a really good approximation of both parts of it, and then just use that as an estimate, right? There are ways to get remainder estimates. I don't really want to go into all that in the class here because it's a rabbit hole that you can go down for a while, but they do touch on it in the book, in the textbook, so I'd suggest giving that a look. But yeah, this is what we can do with power series, right? We can, all those unintegrable functions, we can do now. Right? Right, I gotta cut myself off because I'll talk about that for too long. But any questions here? Awesome. So, let's move on to problem 5. In problem 5, we want to find the Maclaurin series for cosine of x. So go ahead and try and work that out, right? We did the one for sine of x in the lecture videos. Try and see if you can get this one real quick. And I will be right back in a moment. Sorry about that. So, how's it going? So I'm going to quickly draw up this chart that I usually use here. Right, Maclaurin series, so we're finding this at 0. Remember, our ultimate goal here is to find a pattern for these so that we can write down the Maclaurin coefficients. We want to be able to get this formula here. So we can do a few of these, right? As many as we need. So let's see. Remember, the 0th derivative is the function itself. And we go to minus sine of x, minus cosine of x, sine of x, cosine of x, right? And it's just going to start repeating here. So maybe I'll write this, the one for 7. This is going to be back to sine. Right, so here's 2 full repetitions, right? It's just going to keep doing that chunk of 4 over and over and over. So let's plug in these zeros here. Cosine of 0 is 1. Negative sine of 0 is 0. Negative cosine of 0 is minus 1. Sine of 0 is 0. And this is just going to repeat, right? So if we try to write this out as a power series, the best thing to do if you can't make a clean pattern from here is to just write out the parts that aren't 0. Right? So just write out the Maclaurin series. So we'd get 1 plus this coefficient 0, so just 0, and then plus negative 1 over 2 factorial x squared plus 0, plus 1 over 4 factorial x to the 4th plus 0, right? Plus negative 1 over 6 factorial x to the 6th plus 0, plus 1 over 8 factorial x to the 8 would be the next one, plus so on, right? You can see where this pattern's going. And so once you do that, just get rid of all the zeros, and you see this. That was an 8, not a 6. Right, and you start to see this happen. And now you can start to try and find a pattern in here. So here, all of these are even powers, and it's an alternating series that starts with the positive term. So if we start this at k equals 0, we're going to get negative 1 to the k, right? Because that'll alternate plus minus plus minus. Here, the powers are always, 2 times 0, 2 times 1, 2 times 2, 2 times 3. So this is x to the 2k. And it's going to be over 2k factorial, because this number and the number in the factorial always match. Okay. Any questions at all about that? Hopefully that makes sense and looks good. The next part of this problem is verify that this is the derivative of the Maclaurin series for sine of x. Well, all right. So the derivative of sine of x. So if we look at it as a Maclaurin series, that's the derivative of this series. And when we differentiate a series, a power series, again, we can just differentiate term by term. So we get negative 1 to the k times 2k plus 1, x to the 2k over 2k plus 1 factorial. And, well, that will cancel out the top term of this and leave you with a 2k factorial on the bottom. And if we simplify that, that's k equals 0 to infinity minus 1 to the k, x to the 2k over 2k factorial, which is exactly what we just got for cosine x. Wonderful. Any questions there? All right. So some challenges. Verify in terms of power series, in terms of Maclaurin series, that the derivative of cosine is minus sine x. I just gotta check, did I forget to actually write the minus in the earlier class? I did. Good job, me. Right? What is this? Oh god. Yep. So try that, and then a little less of a challenge, but still interesting to try. Verify that the derivative of e to the x is actually still e to the x using Maclaurin series. Right? Make sure that that's still true. Right? All right. So for problem 6 here, right, we want to verify Euler's identity. Right? This is one of the most incredible formulas in mathematics. Right? So e to the I theta is cosine theta plus I sine theta. Right? And again here, I is the imaginary number square root of -1. Right? This formula right here is absolutely surprising that it should even be true. Right? We're relating an exponential function to trig functions. Right? Just because we include this imaginary number, somehow there's this relationship here. Really surprising. Right? So how can we go about this? Well, we can start on the left-hand side with e to the I theta. Right? We have a Maclaurin series for this. Let's use it. That's sum from 0 to infinity of I theta to the k over k factorial. Okay. So let's write this out. Right? I'm going to try and squeeze in as many terms as I can here. So if we plug in 0, this is just 1. No big surprise. Plug in k equals 1, we have I theta. Plug in k equals 2, we get I squared theta squared over 2 factorial. I cubed theta cubed over 3 factorial. I to the 4th theta to the 4th over 4 factorial. I to the 5th theta to the 5th 5 factorial. I to the 6th theta to the 6th 6 factorial. I'm hoping I can get at least 8. Cool. I to the 8, theta to the 8, 8 factorial. All right, that's enough. That's good. I know we just wrote a lot of stuff, but it's okay. Right? So let's look at how these powers of I work out, because something interesting happens here. Right? So I to the first power is just I. Right? I to the second power, remember I is square root of -1, so that's -1. That means I to the third power is minus I. And that means I to the fourth power is going to be -1 times -1, so it's just 1. So then I to the 5th power is just I. I to the 6th power is -1. I to the 7th power is going to be -I, right? And you get this kind of repetition here, this cycle of 4 that goes on. So let's get rid of all these powers of I then and turn them into just 1 or I. So here we'll get 1 plus I theta. This will be minus theta squared over 2 factorial. Here, this is minus I times theta cubed over 3 factorial. And then I to the 4th is just 1, so plus theta to the 4th over 4 factorial. Plus I theta to the 5th over 5 factorial. Right? You can see where this is going. Minus theta to the 6th, 6 factorial. This will be minus I theta to the 7 over 7 factorial. Plus theta to the 8th over 8 factorial, and so on. Right? Now here's the fun part. Let's look at all the parts that don't have an I in it. We got this one, this one, this one, this one, and this one. Right? Let's look at all the parts that do have an I in it. This one, that one, that one, that one. Right? What we're going to do is we're going to group them together. Right? So all the blue ones, let's group them together. We got 1 minus theta squared over 2 factorial plus theta to the 4th over 4 factorial minus theta to the 6 over 6 factorial plus theta to the 8 over 8 factorial dot dot dot. Right? And then plus. Now all of the red ones have an I in it, so let's factor out the I and then write down what we have. Well, here we get theta. Here, minus theta cubed over 3 factorial. Here, plus theta to the 5th over 5 factorial. This one, minus theta to the 7 over 7 factorial. Dot, dot, dot. Right, so something really interesting happens here. What is, in blue here, what is this power series that's been formed? Right here. All this stuff, what does that make up? In blue, what is that? Once you figure out what that stuff in blue is, what is the stuff in red? At least inside the parentheses.
Is it cosine theta?
Yep. Yeah, this stuff in blue, this is exactly cosine theta. And then if you look at the terms in red, you get I, this stuff right here. These are the terms of sine theta. And there we have it. E to the I theta is cosine theta plus I sine theta. And that's how you can verify this fact. And just as a sort of a way to sum this up, let's plug in theta equals pi. This gives you cosine of pi plus I sine of pi, which is just -1 plus 0. So this gives you this formula here, which is known as the most beautiful formula in mathematics. Because it relates e, I, pi, 1, and 0 all in the same equation. All of these sort of famous constants of math all together in one equation. Right. So quite a bit of interesting stuff going on here that we can only, unfortunately in this class, only just barely begin to touch on. Right. Well, any questions here? All right then. Well, I think then that is it for the class for today, or for the problem session. I finished recording the lectures for tonight right before class started, so I didn't have a chance to post them, but I'm going to do that literally right after I hit end stream. So, unless anyone has any questions, have a great afternoon. I hope you've had a good weekend and your week's going well so far. But thanks for stopping by. See you tomorrow.